Okay, so I would like to invite the next our presenter, Mr. Colin Clarke. He will be presenting on the topic of increasing the processabilities and performance characteristics of natural rubber containing compounds.
Okay, good morning everybody. We're going to jump back to materials away from machines, but in a way actually a very good connection to the previous speaker, because I guess with steel cord processing and belt processing we're talking about predominantly natural rubber. And I'm going to tell you how you can process your natural rubber to run it through the advanced machines that Seilacher can offer. So it's a good connection, I think. Okay. So yeah, we're going to talk about improved mastication efficiency, the breakdown of natural rubber. We're going to talk about mill room productivity, and we're going to talk about optimized dynamic properties finally in the natural rubber to especially contribute to fuel saving and low hysteresis within the tyre, let's say. So why natural rubber? Well, of course, this is the preferred polymer for a lot of engineered solutions, high molecular weight, very stereoregular with good strength, low hysteresis. But of course, we have to process natural rubber with extra processing steps in order to be able to calender it, extrude it, and to work with it. So really to talk about how we can introduce in the most efficient way that extra processing step, the rubber breakdown stage, into natural rubber compounds. So generally for this we're using a material called a peptizer. Peptizer is a chemical that can be used to chemically break down, to cleave natural rubber chains, to reduce the molecular weight and therefore reduce the viscosity of natural rubber. This is great because it makes the rubber processable, but actually in a way also then harms the very good stereoregularity, the high strength properties of natural rubber. So we really need to balance the usage of our chemical peptizers in order to achieve good processing whilst maintaining the better dynamic properties and good strength properties of natural rubber. So a lot of different chemical peptizer technologies, and this presentation will contrast a couple of the different options that are available to you. So as mentioned, natural rubber really needs a pre-mixing stage. We call it pre-mastication. This is, where's the pointer gone? Ah, yeah, okay. This is the extra stage, if you like, which is really traditionally, historically, a rubber breakdown stage. So we put rubber in our mixers, we masticate, we break the natural rubber down, we move it then out of the mixer. At this point, we did no compounding. We just did rubber breakdown. We might add a little bit of filler, but essentially we didn't blend with polymers. We didn't do anything to move that compound towards the next stage. And then we have subsequent stages, compounding, filler addition, and cure addition stage finalizing. And generally, we would use conventional peptizers in this stage, a couple of minutes, maybe minimum, to break the natural rubber down. But actually, if we want to skip this stage, this is an extra stage, this is a stage where we don't achieve any real productivity, we just prepare the natural rubber for mixing with other polymers. If we want to skip this stage, if we want to make the process more efficient, we have to find a way to peptize, to break down the natural rubber and compound in the same stage. And this is really the target to improve the efficiency, if you like. Oops. Okay, so actually then, if you like, just to highlight that, let's jump in quickly, sorry. We start with our mixer, we add natural rubber, we break down, we move it into another stage, we add fillers, carbon black, and then we add the curatives. So essentially, we have 3 mixing stages, and the first stage really just breaks the natural rubber down. This is relatively inefficient, long-term processing, and in a way, really multiple mixing stages will tend to degrade our natural rubber properties. Our target, therefore, is to combine the peptizing, the filler addition and the polymer blending into one stage. So can we bring these 2 stages together? Can we eliminate a mixing stage? Can we save all of that energy, if you like, and put it into one mixing stage? So effectively, with chemical peptizers, we can do that, but we're very limited. Chemical peptizers should not attack the synthetic polymer. The chemical peptizer is, in a way, deactivated when we add carbon black. So we're quite limited in this so-called in situ mixing, same stage, that we have to complete that really in the very, very early part of the mixing, because when we add carbon black and the other ingredients into that, we lose the peptizer efficiency. So actually, can we really maximize the behavior, if you like, the way of working of the peptizer by changing the technology a little bit? So actually, new technology, we call the product HT105. It's a series of new generation peptizer, natural rubber breakdown chemicals that is much more tolerant of the presence of carbon black, and in a way will much more selectively target natural rubber and will not cause any adverse breakdown towards the synthetic rubber components that you have. It's also much less temperature sensitive, so variations in temperature as you start with a half-filled mixer, you add your carbon black and ingredients later in the same stage, the temperature variation is greater, but the new peptizer is much more tolerant of that as a chemical change, if you like, than you would have with a conventional chemical peptizer. So let's take a look at how these products work. We have conventional chemical peptizer, we call it Struktol A86. This is a product in our range, very similar to many peptizers that you'll find on the market today. They all work in the same way. They have two components. One component is an activator. It generates free radicals that attack natural rubber double bonds and break the chain down. The second component is a radical stabilizer, because every broken chain must be stabilized or we form branch polymer, which we really don't want for natural rubber. So we have two components. Alongside that, we could use, and many people talk about, we don't need aggressive chemical peptizers, we can use some kind of lubricant, some kind of physical peptizer that people talk about, some kind of viscosity reducing agent to improve the processability just by improving the slip in the natural rubber. So zinc soaps are often used for that, so we'll contrast the conventional chemical peptizer with a very conventional, if you like, traditional zinc soap, and then we'll introduce, oops, it's very sensitive, we'll introduce the new peptizer, product called Struktol HT105, and look at how that can be much more efficient and actually give us a better property profile overall. One of the ways that we can look at that is to do natural rubber breakdown in a very small mixer. One of the smallest mixers on the market with very accurate measurement is a Brabender plastic order. So it's about 100, 150 grams of rubber with a very accurate temperature control and a very accurate energy measurement. So we'll do mastication studies under very controlled conditions and look at the rate of breakdown of natural rubber. So first of all, if we break down natural rubber with no additive at all, we just let the rotors do the work, we see the energy reduction, we see the torque reduction as the natural rubber softens and breaks down slowly. So that's mechanical mastication, no additive whatsoever. If we had a chemical peptizer, then as the temperature rises, about 100, 110 centigrade, peptizer becomes active and the torque drops quite quickly because the peptizer attacks the natural rubber, we break the chains, molecular weight falls and the viscosity comes down. So that's quite nice. A physical peptizer does exactly what we say. Actually, it's just a lubricant. There's no chemical attack at all on the chains. So it's very similar to the mechanical mastication. We see a little bit of slip action at the start, the torque falls. Slip between the rubber and the rotors. Physical peptizer is very rubber soluble. It's absorbed back into the rubber very quickly. So we see the torque return. But it pretty much follows the line of the mechanical mastication. So virtually no breakdown at all. Oops. Okay. And then finally, if we add in then the HT105, the new generation peptizer, it pretty much follows the line of the chemical peptizer. So it has a strong efficiency to reduce the viscosity of the natural rubber, to reduce the energy required for mastication. What does that mean? So this is the rubber before breakdown. Mechanical mastication, of course, reduces the Mooney. We use the energy to break the chains, Mooney comes down. The zinc soap, the lubricants, hardly any difference to mechanical mastication, little bit of slip action, slightly lower viscosity, but not very efficient. The chemical peptides are very strong, so we've almost halved the viscosity relative to the control compounds, if you like. And the new technology product, very similar. The energy curves you saw mixing were similar, and it's no surprise that actually the Mooney viscosity is the same as well. So we can achieve the same kind of breakdown just with natural rubber, no other ingredients added, so we allow the peptizers to work to their full extent. So that's fine. But let's go now into a compound and see how that looks. So a very simple compound, 100% natural rubber, a little bit of carbon black, small amount of oil, very standard cure system, semi-EV curing. And we'll do the pre-mastication. So we'll do the first stage mixing, rubber and peptizer, take it out, add the carbon black in the second stage, and finish the compound with the accelerators in the third stage. So that's the very traditional, more time consuming, more energy consuming, three-stage mixing, if you like. Actually, when we do that and we look at the first stage of mixing, just the rubber mastication, we can measure the molecular weight reduction. So not only Mooney, but also what did we really do to the molecular weight. So these are the molecular weight distribution curves. You can see the control compound before mastication in black. We have some very long chains in natural rubber, more than 10 million units. And we want to reduce this long chain material. This is difficult processing, very, very high viscosity components, but we don't want to increase too much the short chain material because this harms the strength and the elasticity of natural rubber. Unfortunately, our chemical peptizer, a very random product, attacks natural rubber on every double bond. So anywhere there's a double bond, potentially can break. Long chains get smaller, short chains get progressively more smaller. So actually, our molecular weight distribution gets wider. And we see that very much with the red curve. So we reduce the long chain material, but we increased with the chemical peptizer the short chain material. By contrast, mechanical mastication, just the mixer itself, statistically, oops, my fingers are too big, I think I catch the wrong button here. Statistically, we break down, preferentially we break down the longer chains more than the shorter chains because longer chains are more entangled, and when we apply shear forces, stress forces, they break preferentially. So actually we reduce long chain material, but we don't increase the short chain material too much. This is good for dynamic properties. And actually our HT105 pretty much mimics what we had with mechanical mastication. But if you remember the energy curves, mechanical mastication was very high, the new peptizer was very low energy. So we have a breakdown that looks like a chemical peptizer, but a molecular weight that looks like no peptizer. So this is already a good sign for good processing and good properties. So this is really the best of both worlds a little bit. And actually we can confirm that because when we finally look at Mooney viscosity, chemical peptizer and HT105, exactly the same, but dynamic properties or molecular weight, if you like, looks like no peptizer present. So that's good. Oops, come, go. Looking at physical properties, I'm not going to read out all the numbers, but they're approximately similar. You can imagine that we have the same level of breakdown, we have the same behavior, a little bit inferior aging properties for the chemical peptizer, but essentially the same. If you want to discuss in detail the numbers, come find me on the Gibson booth. I'm very happy to go through all the details. But let's look at the dynamic properties because it's quite interesting. Natural rubber, it should be then a low hysteresis, energy efficient polymer, and we can measure that with breakdown, looking at Goodrich flexometer, looking at the heat buildup and the blowout for a high severity fatigue test, if you like. So the control compound, a chemical peptizer, sorry, quite a high heat buildup and a very short blowout time, so failure fairly quickly if we apply the high load. Mechanical mastication, it's better. We are not breaking the chain so aggressively, so we have a cooler compound, longer blowout time. But actually, the new product gives us a better dynamic property, so even lower heat buildup and a longer blowout time. So it actually stabilizes the natural rubber. We have a much narrower molecular weight distribution. But actually what's really interesting is to look at, that was conventional mixing. We didn't save any time, we didn't save any energy. And you guys would say, why would you buy this new product? Because there's no real saving on the table so far. But let's look at a step cut. Can we combine the two processes into one? Can we do mastication, breakdown, and mixing in the same stage? And we can, so we take the same compound, and now we're going to do mixing and carbon black addition in the same stage. So we start with natural rubber, we add the peptizer fairly quickly, we add the carbon black, and we finish the compound only in 2 stages. Some canny companies, some smart companies might say, actually I don't need any peptizer, let's just mix for a little bit longer. Why worry about that? We have more time, we have more capacity, I'll just extend the mixing because this will break the natural rubber down more. So okay, we'll look at that, we'll do control compound, mechanical mastication, for 3.5, 4.5 minutes. The others are 3.5 minutes each, and we'll compare those. But we add the 2 products right at the start, and then we add the carbon black in the same stage. So we're really shortening, we've eliminated the pre-mastication. Now let's look at the Mooney viscosity. So this is our mechanical mastication, 3.5 minutes. Come on, jump, go, more, okay. 4 minutes, 4.5. And of course, extending the mixing reduces the viscosity, but it's not that strong. It's just a little bit down. If we compare now the chemical peptizer, like we saw in the first study, a big reduction in viscosity because it really did chain breaking, and that brings us in the viscosity range where we can really process and extrude or calendar the natural rubber compounds through the nice machines that Seilacher can offer. But now look, what happens with the new product, because we added carbon black, we effectively stopped the chemical peptizer working. We don't have that condition with the new product, so we can continue viscosity reduction, where in the first study the Moonies were the same, now the Moonies lower, because as soon as carbon black hit the system, it deactivates the conventional chemical peptizer. So now we have a better processing because we can control our Moonie viscosity and extend it beyond that, if you like. Physical properties, now we can see some slight differences, so slightly higher tensile strength, elongation at break, because of the aggressive chemical action, which we eliminate with the new product. But what does that mean in real world? We talk about Moonie viscosity, but what does it mean really under a cold feed extrusion? So we have small Brabender extruders, we have a lot of measurements. I'm just going to show you the output for the same conditions, so same screw speed, nominally the same pressure. If we look at the extrusion for the two control or the three additives, of course, very minor increases in extruder output. The line speed hardly changes at all. We had a little bit of reduction in viscosity when we just extend the mixing without additive. Of course, chemical peptizer gives us a big improvement with 50% more line speed, if you like. But actually, the new product really doubles that because we have low Moonie viscosity, we have a lubricating action, we can really make the compound flow, and that's to be beneficial for our processing. Of course, then we want to balance that against good dynamic properties. And first study, we looked at a very high severity test, the blowout test, if you like, with the flexometer. But actually, we don't really want to fail those compounds. So one other way to measure that is to just look at the tan delta, the hysteresis at 60 degrees centigrade. And any reduction in tan delta means a lower hysteresis. It means an energy-saving component. So we have less heat build-up in that component. If we index the control compound, so the control compound, no peptides at all, 3.5 minutes. As we increase the mixing time because of better breakdown and dispersion, for sure we reduce our hysteresis, we reduce our tan delta. But by contrast, the chemical peptizer actually increases that hysteresis. We generate a lot of short chain material and branch polymer, and our heat buildup potential in the natural rubber increases. The new product gives us the lowest heat buildup of all. Not only do we have lowest Moonie viscosity, best flow properties, best extrusion, we actually have the coolest running compound, lowest hysteresis, best energy saving performance. So actually I would say for this product we can reduce viscosity at least as efficiently as we can do with conventional peptizers. We can certainly offer you the potential to have a step cut. You don't need to do pre-mastication, you don't need to do rubber breakdown. So this is an efficiency saving, this is an improvement in processability, you can improve your extrusion efficiency, and of course you can lower the heat buildup in your tyre. So this is really a win-win situation, if you like. And with that, I would say thank you very much for your attention. Hopefully it was fast enough. I know you're short of time.
Thank you very much, Colin. Okay.